Hello, Honors Chem students. Mr. Keister here with you today. This is the video for Friday, October 2nd, 2020, which is our scheduled 31st day of school for the fall semester. Keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented are going to remain the same regardless. I'm wearing a shirt and tie today. Don't get used to it. I'm not really into wearing shirts and ties anymore, but it seemed like a good day to do it. It's technically today is picture day, so you kind of know when I'm making this video. So wanted to look good for the part. You know how that goes. So anyway, let's look at today's do nows and see what our schedule is for today. Today you picked up three things. Energy bar diagram PowerPoint notes. How to set up an energy bar chart. It says LOL. Wonder what that means. And the energy bar charts assignment. Your homework for today was to complete the thermal energy, phase energy, and heating and cooling curves assignment that we went over yesterday. I'm not collecting that, but you absolutely need to know how to make a heating and cooling curve and how to identify it, how to interpret it, and how to draw one correctly given a particular situation. So those are very important to our study this unit. Make sure you know how to do that. Of course, the answers are on the board in the back here in class. If you're home, those answers are posted to the answer keys page on Canvas. Make sure you've checked this one. Today we're going to continue with the second half of Unit 2 regarding energy. We're going to learn how to set up an energy bar diagram and an LOL chart. LOL, wonder what that's about. You'll have an assignment over this that is due on Monday, okay? Also, don't forget, you have extra work to do outside of class. The Unit 1 and 2-1 review assignment is the first review out of 3 for the fall semester final exam. You're going to be working on that on your own time. I hope you already are. It is due this coming Tuesday, all right? This coming Tuesday at the beginning of class. And as I said yesterday, there will be no answer key posted for this. All my reviews for the finals, no key, all right? So I suggest you communicate with friends and classmates as you work on it so that hopefully you can check each other and catch each other's mistakes and figure out who's right and who's wrong before you turn it in, all right? You want to make sure it's accurate. These things are worth a lot of points. So I think that's it for the instructions. So let's get to today's lesson. All right. So an energy bar chart, these are from the PowerPoint notes you picked up today. So an energy bar chart is how to represent the role of energy in a physical change. So we're going to be dealing with physical changes in this unit. Chemical changes, which of course involve chemical reactions, are going to come a bit later. All right, so that's what we're going to do first. Look at physical changes and how energy plays a role in those changes, because it most definitely does. Constructing an energy bar chart, all right? So it says, consider this example. A cup, let me put this down just to here. There we go. Consider this example. A cup of hot coffee cools as it sits on the table, all right? A cup of hot coffee cools as it sits on the table. Determine what is in the system. Well, it's coffee, all right? Coffee's our system. What happens to it? Well, it cools down. It's a physical change, all right? It was coffee before the change started, and it was still coffee after the change ended. So what we're going to do is determine the role of energy in this change as this coffee cools. So before we get to that, I'm going to, I want you to pull out one of the other papers in how to set up an energy bar chart, all right? So let me pull that document up real quick, and then we'll come back to this one. There it is. Setting up an LOL. Why do I keep saying LOL? It's not that funny, at least not yet. All right. Setting up an LOL energy bar chart. Well, the secret will be out here in just a minute. So yesterday we talked about thermal energy. All right. Thermal energy occurs when changes in temperature happen. So thermal energy, we know, is changing when the temperature is changing. So we're going to set up some parameters here for bars. Energy bar chart. Yes, this looks a lot like a bar graph. We use bars, and that's why it's called that. So hot is 4 bars. All right. So what is hot? Well, if it's greater than or equal to 100 degrees Celsius, then we will consider it hot. Or if the problem just says it's hot. All right. So if it says it's hot, it's hot. We give it 4 bars. If it gives us a temperature, if it's 100 degrees or higher, then we are going to call that hot. Okay. Warm, 3 bars. Okay, so warm will be greater than 25 degrees Celsius, all right, but less than 100 degrees Celsius. So if we're between 25 and 100, all right, above 25 or less than 100, then we will assign that situation 3 bars of thermal energy. Room temp. 2 bars. Okay, so if it says room temp, we go with 2, or if we are between 20 and 25 degrees Celsius. So 20 to 25, that is considered room temp. That's actually around 70 degrees Fahrenheit, a few degrees above, a few degrees below. All right. Cold, 1 bar. So again, if it says cold, we'll assign it 1 bar, or if it gives us a temperature and it's greater than or equal to 0 degrees Celsius and less than 20, then that is cold, all right? If we run below 0 degrees Celsius, we're going to give that a half a bar, all right? Below 0 degrees Celsius, we're going to give that a half bar. And as we said the other day, all right, when we were talking about, well, this would have been a week or so ago when we were in our study of gases, the temperature at which there is no energy, all right, is 0 Kelvin, or absolute 0. At that point, 0 bars, all right? You need to memorize these, okay? So make sure you know the parameters for setting up the bars of thermal energy, okay? Next, we're going to deal with phase energy, okay? Okay, so a change in phase energy occurs when the phase or state of matter changes. So when we're going from solid to liquid, liquid to gas, or the other direction, gas to liquid or liquid to solid, then we're undergoing a phase change. Remember, during a phase change, the temperature remains constant, all right? Because the energy involved in the phase change is phase energy, not thermal, all right? So remember, I told you too that some texts, told you the other day, yesterday actually, that some texts refer to phase energy as interaction energy, because it involves the interaction of the particles as they're getting closer together or spreading farther apart, which is what happens during a phase change. So some texts or references, you might hear that term. We're going to use phase energy. So gases, we'll give 4 bars of phase energy. Remember, gases have the most phase energy. Liquid, we're going to drop it to 2, all right, because the phase energy between liquids and gases is quite different. The phase energy from liquids to solids is not that different, all right? Remember, the spacing in a liquid as compared to a solid is not all that different. And so we're going to give solids 1 bar. So solids 1 bar of phase energy, liquid 2 bars, gas 4 bars, all right? Again, gases have the most phase energy because they have the most freedom to move about. The more freedom you got, the faster you can go because you got more space to move, all right? And then finally, down at the bottom, chemical energy. And we mentioned this too yesterday. Chemical energy is a measure of the strength of the intramolecular attractions, which we call bonds, all right? This changes only when the identity of the substance changes. So we're going to look at phase or chemical energy in another unit, all right? So we're just dealing with physical changes in this unit in regards to energy change. So For now, chemical energy we're going to leave alone for the time being. So this is how we set up the bars for thermal energy. This is how we set up the bars for phase energy. All right. Remember these. Got to commit them to memory. Now let's go back to our PowerPoint presentation. Erase that. So a cup of hot coffee cools as it sits on the table. So we're going to determine what's in the system. Oh, LOL charts. Well, do you see it yet? See it? L, O, L. There it is. All right. So the system is the O. All right. The system is the O. Our system now is a cup of coffee. That's what's written in there. All right. Everything else involved in this situation makes up the surroundings. All right. Let's go to the next screen. So there is no chemical energy involved, as we mentioned a little bit ago, because this is just a physical change going from warmer to cooler. All right. We had coffee before the change started. We have coffee after. And so the particles are not rearranged into some new substance. So no chemical energy is involved. All right. Assign values to phase energy. All right. So we started off with warm or hot coffee. All right. That's in the liquid phase. How many bars of energy did we say we do for the liquid phase? And the answer to that is 2. All right. How is coffee when this is all over? Well, it's cooled down, but it's still liquid coffee. So before the change, it's 2 bars of phase energy. And after the change, it's 2 bars of phase energy. All right. So, as we just said, we have done this now. So I want you to look at this a little closer. So again, L, O, L. The system is the O. In this case, it's the cup of coffee. The first L are the initial conditions. All right, the initial conditions. The last L are the final conditions. Then we have areas here, 3 areas, 3 columns basically. Thermal energy, phase energy, and chemical energy on both. Again, chemical energy we're ignoring because there is no change in chemical energy because there's no change in identity. So, but there is now, we have assigned the bars for the phase energy for this coffee. It was a liquid before, which is 2 bars of phase energy. It was a liquid after, so it's still 2 bars of phase energy after. All right. So now we're going to go to thermal energy. So it said the coffee was hot. So it didn't give us a temperature, but it said it was hot. So we're going to assume it's 4 bars. All right. As we said a little bit ago in setting up thermal energy. So we're going to use 4 bars for hot coffee initially. So under our initial L here, under thermal energy, we draw a bar that's 4 high. All right. Remember, 4, 3, 2, 1. They're not numbered there, but that's how it's set up. We'll do that now so we can remember that. Okay. So we had 2 bars of phase energy, both before and after. And now, initially, we have 4 bars of thermal energy because the coffee's hot. And then when it has settled down to room temperature, which is how the system ended, we then have 2 bars of thermal energy in our final L under thermal. All right? Next. Now we're going to show the energy transfer. So this just involves simple addition and subtraction. So pay attention. Here's how we're going to do it. So we check and see how many bars of energy we have in our initial conditions. Well, we have 4 bars of thermal, 2 bars of phase, for a total of 6 bars. So underneath our initial L, we write 6 bars. Go to the final. Well, we have at room temp, we have 2 bars of thermal energy, and we still have liquid coffee, 2 bars of phase energy, for a total of 4 bars. So you write 4 bars underneath the final. So now let's take a look and see what happened. So we started with 6 total bars of energy. We ended up with 4 total bars of energy. What happened? So between 6 and 4, what happened? Well, let's see. 6 minus 4 is 2 bars. So we lost or released 2 bars of energy into the environment, which is exactly what happens when something cools. All right, so when the coffee starts out hot and it ends up room temp, what happened to the energy that it lost? It went up into the surroundings, okay? So underneath the energy flow, underneath the O, we write minus 2 bars. Like a simple little math equation. 6 bars minus 2 bars equals 4 bars. So now let's go up to the O. We lost 2 bars of energy to the environment. We want to show that right here. So here are our 2 bars. So we draw a little boxy arrow here that's approximately 2 bars in length, because that's what we lost. And notice that it's pointing outward. All right? It's pointing outward towards the surroundings, out of the system. All right? So this is 2 bars out. All right? 2 bars out. We call this Q. All right? Q is a combination, as we said yesterday. Q is a combination of thermal energy, phase energy, and chemical energy. All right? We didn't have a change in chemical energy, but we had a change in the other 2. All right, of the other 2 combined. And so we label this Q. This is the total amount of energy. Q we basically just call heat energy, which is a combination of all 3. All right. So we're showing Q going out into the environment, into the surroundings of approximately 2 bars. All right. So as something to note, as something cools. All right, as something cools, energy flows out into the surroundings. We have a term for that in chemistry. When energy is flowing out of the system, we call that process exothermic. When energy is released by something into somewhere else, that process is called exothermic. All right? So this is an LOL chart, an energy bar chart. All right? Let's go on to the next one, shall we? Now we're going to consider a phase change. All right? A tray of ice cubes, initially at -8 Celsius, is placed on the counter and becomes water at room temperature. All right? What do we know about this situation? Well, the system is a tray of ice cubes. All right? So ice cubes is our system. That's going to be the O, all right, in the LOL chart. The solid water turns to liquid water. There's no change in chemical energy. Ice cubes and liquid water are both H2O. No change in identity. This is a physical change only. So again, we can ignore chemical energy in this situation. The phase energy is going to increase because we're going from a solid to a liquid. All right? We'll designate that in our chart here shortly. And the thermal energy is going to increase because the temperature is rising. All right? So let's represent those changes in a bar graph, in an energy bar graph. All right, so what's going on here? Whoops. There we go. All right, so let's do thermal energy first. So we're starting at -8 degrees, all right, -8 Celsius. How many bars does that get of thermal energy? Well, we said if it's below 0, it gets a half a bar. So down here under thermal energy, again, this is 4, 3, 2, 1. Here under thermal energy, we just have a half a bar, all right? How does it end up? It ends up at room temperature. So our thermal energy in our final stage over here in our last L is going to be 2 bars, all right? As we have right here. So a half a bar for -8 degrees initially, 2 bars for room temp finally. Again, our system is the ice cubes, okay? And so we label our O as such. So that takes care of the thermal energy. Now, what about the phase energy? Well, we're starting out as ice, which is a solid. How many bars of phase energy does a solid get? And the answer is 1, all right, 1. We end up as liquid water, all right? And so now we're in the liquid phase. How many bars of phase energy does the liquid phase get? And the answer to that is 2. And so 1 bar of phase energy for solid initially, 2 bars of phase energy for liquid finally, okay? So what do we end up with? Well, let's look. Again, this is just very simple math, all right? So we have a half a bar of thermal and 1 bar of phase initially for a total of 1.5 bars. We have 2 thermal and 2 phase finally, which is a total of 4 bars. And to get from 1.5 bars to 4 bars, well, looks to me like we're adding energy, all right? In this case, 2.5 bars. So here again, write this at the bottom. 1.5 bars under initial plus 2.5 bars under energy flow, under the O, equals 4 bars, or 4.0. I guess they're keeping all the precision levels the same, which is a good idea. 4.0 bars under the final, all right? So now we have gained energy. Where from? Where does it come from? When you put ice on the counter and it melts, where's the energy that it absorbs coming from? It's coming from the surroundings, all right? So on our energy flow here, we're showing about 2.5 bars long, okay, of energy coming into the system. Notice the arrow is pointed in towards the O, not out like it was before, all right? And so Q, which again is a combination of all our types of energy, is coming in 2.5 bars. So we got 2.5 bars in, okay? Okay, so as something warms, all right, energy flows into the system from the environment or the surroundings. And we got a term for that in chemistry too. Those types of processes are not called exothermic, they are called endothermic. Endothermic, all right? So, I think that's what we got right there. So, let's go to our homework. I want to look at the first one together, look at the directions, and make sure we've covered everything it says to do. All right? So, let's look at that next. Okay, here it is. So let's look at the directions. For each of the situations described below, use an energy bar chart to represent the ways that energy is stored in the system and flows into or out of the system. Be sure to, number 1, label the system. That's the O. Number 2, show up the transfer of energy as exo or endothermic. We're going to write in our bar situation down here, just as we did. We're going to write that the energy is flowing in or out, and we're going to label it as exo or endothermic. 3, below each diagram, show how the first law of thermodynamics applies. That's the law of conservation of energy. That's writing our little equation down here that we just talked about. And number 4, sketch a heating or cooling curve for the situation out in the left margin. Okay, so this is in addition to what we learned yesterday. All right, so we're going to kind of combine what we did yesterday with what we learned today. So the first one actually is the first example we did on the PowerPoint notes today. So we're just going to redo that one and then finish it off with the additional things that we're asked to do. All right, so it says a cup of hot coffee cools as it sits on the table. So it's going to cool to room temperature. All right, so again, 4, 3, 2, and 1. You can label those if you want. So our system is coffee. You want to label that first. Okay, let's start with thermal energy. So hot is 4 bars. So I'll draw in my little 4 bars there. I'm not the greatest colorer in the world, but it's good enough. And it's going to end up at room temp. So that is 2 bars of thermal. So there's my 2 bars there. Coffee is a liquid. Phase energy for a liquid is 2 bars. It's a liquid both before and after. So 2 bars of phase before, 2 bars of phase after. All right. So next, let's total things up. So we have 6 bars here. We have 4 bars here, which means there is a loss of 2 bars of energy during this process. So minus 2 bars equals 4. So now we need to represent our loss of 2 bars in our diagram here. All right. So I'll make a barred arrow, approximately 2 bars in length. Just do that the best you can. And we lost 2 bars, and so that energy is going out. So the arrow's got to point out away from the system into the surroundings. Again, this represents Q, which is a combination of both types of energy involved here, thermal and phase. Of course, chemical energy is also a part of Q, but we don't have a change in that. And so flowing out of the system is exothermic. So make sure you label that. So let's see. We've labeled the system, coffee. We've showed that the transfer of energy is exo or endothermic. We've done that right here. Below each diagram, show how the first law of thermodynamics applies. We've done that with our little equation here. And lastly, sketch a heating or cooling curve for the situation out in the left margin. All right, so let's do that. So remember, we have temperature in degrees Celsius on our y-axis. We have time on the x-axis. Okay, we're not given specific temperatures, all right? If we were, we would label them as such. All we're given is a situation where we're starting hot and ending up at room temp. So I'm just going to arbitrarily, since it's hot, I'm going to put it up here. And since I don't have a numerical value, I'm just going to call that TI, T initial. All right. Remember, this is initial and final. We don't know what that temperature is. We know it's hot. All right. So what happens is it goes to room temperature. It cools down. So arbitrarily, and it takes some time to do that. All right. So arbitrarily, I'll just put down here lower. I don't know where it would be exactly, but we'll just put T final there. If we knew what it was, we would label it as such. Of course, it takes some time to do that. And so it's not a vertical line. That would mean it happens instantaneously, which it doesn't. And so we draw our line here. Remember, it should have a negative slope. We're losing energy. All right. And so, and what type of energy change did we have here? Well, remember, there was no change in phase energy. Remember, a change in phase energy, it results in a phase change. Remember, that's a horizontal line. That's not happening here. All right. So this is simply a change in temperature, which is a change, as we see on our bar graph, in thermal energy. So we've taken care of that. So I think we are good to go with that one. Follow these same directions on the others and complete the homework assignment for tomorrow. You might want to have your assignment from yesterday nearby, where you have all those graphs, you know, of heating and cooling curves. You might want to use that as help as you check your situations in all of these problems, because in some of them, a phase change is involved, and so you want to make sure you're doing that correctly as well. As far as labeling these, if you're given temperatures, then they need to be on there. If not, you're just going to have to deal with T initial and T final, right? And then make sure you label the type of energy that is involved on the graph itself, okay? And in some of these, you might have a couple of steps. And so the type of energy involved in those steps may be the same, may be different. So again, refer back to your heating and cooling curves from yesterday. That will help you, okay? So I think that's it for today. So on this assignment is due tomorrow, or it's due Monday. Sorry, today's Friday. And so until next time, this is Mr. Keister signing off. Stay safe, everyone. Keep working hard and stay focused. And I'll catch you next time. Without a shirt and tie. See ya, guys.